roll is done. So I was lurking and overheard something, and so I explained something poorly previously that I need to address. And it has to do with the gain of a half circuit and using that to give you the gain of the full differential circuit, okay? And so effectively, the mistake that I made in explaining it, so let's say we have a very simple circuit, right? We have a differential pair like so, where we have some resistance RD. And then here is our input for M1. Here we have VDD. Here's RD. Here is M2. And then down here is our tail current, ISS. Okay, so if we apply 1/2 VIDM here and negative 1/2 VIDM here, if we look at the half circuit, that would be VDD times our resistor. Excuse me, there's RD. And 1/2 VIDM here. Okay, and sorry, here is V out 1. And here is V out 2. So this guy would correspond to V out 1. As we know, this is simply a common source amplifier. And so the voltage gain of this circuit, so here's where the problem arose from, okay? V out is supposed to be Vn, which is 1/2 VIDM times the gain, which is GM1 in this case, R01 in parallel with RD. And so I suggested that you multiply the gain by a factor of 2. What I did not include explicitly here was that we're only applying half of the differential mode signal on each side, okay? So if we considered a case where all of the differential mode signal were applied to the input of M1, we would get the exact same result as just the gain of the half circuit being the gain of the differential amplifier. Does that make sense? So effectively, if we treat this instead of as 1/2 VIDM as just all of VIDM, this gives us the voltage gain of the differential circuit. So there was a factor of 2 that I was lazy about explaining where it came from, and it caused some confusion. So my hope is to rectify that. Effectively, if you analyze the half circuit with Vn applied to the input terminal and V out taken at the output terminal, you get the gain of the differential circuit. Is that clear? So on homework 3, I'd be willing to bet that if the answer that you were getting was twice as large as you expected, it's because I explained it poorly and I'm trying to rectify that right now. Okay, are we comfortable with that? Okay, now it's time for you guys to ask me questions because that's what today is for.
Can we ask about the homework?
Absolutely.
Number 2 on homework.
It's challenging.
Yeah.
I wouldn't,
But you said homework 2 is straightforward.
homework 2 was straightforward.
I struggled.
Okay, well, all right. Homework 3, problem 2. Let me pull that up just so that I redraw the circuit correctly. Actually, I think I remember it. Something like this, right? Where we have, it was a BJT, right? Or was it a MOSFET? Was it a PNP or an NPN? This is R1. Here's the out one. Here's the in one. I'm gonna make this crazy wide so I have enough space. Okay, if I'm not oh, and I need to call this over here VN2, and this is VCC or VDD. I don't particularly care, and it doesn't particularly matter. So this is part A, I believe. So in my opinion, this is the harder of the two circuits that I asked you to analyze. So let's start. Is it symmetrical? Yes. Okay. So that means our half circuit is supposed to look like this. Okay. So I believe I suggested this to you in class, but we are going to use the short circuit transconductance method to figure things out here. Okay. So the first thing we're going to do is calculate our short circuit transconductance by using the small signal model of this guy. So I'm going to start by drawing our small signal model. So let's call this guy M1 and this guy M3 so that this guy is M1 and this guy is M3 so that I can be consistent. So let's say that this is GM3, VBE3. Here's R03, which makes this terminal up here the collector of transistor 3. Here's R pi 3. Here's VBE3. And then this is our base for transistor 3. And this is our emitter for 3. And the base is our output node. We're going to get to M1 in a minute. But the base is our output node, right? The base of transistor M3 is our output node.
Yes.
If we're using the short circuit transconductance method, we short circuit the output node. Measure the current flowing in the output node, which I'm going to call I out. Now, between our base terminal and ground, we have a resistor R1, but it's grounded on both sides, which is why I'm not drawing it, because it doesn't do anything. Are we okay with that? So because it's grounded, it's at AC ground here because we're doing the short circuit transconductance, and it's at AC ground here, R1 shouldn't show up because it doesn't contribute anything. So it's just there to be confusing. Okay. Our collector terminal, which is this guy right here, is also at AC ground. So I'm gonna just ground this guy over here. And our emitter terminal is connected to the collector terminal of M1. So now I'm gonna draw the small signal model for M1 down here. This is the collector of 1. It's tied to the emitter of 3. Here is R pi 1, excuse me. Here is VBE1. Our input signal is applied to the base of M1. So here's VN. This is the base of 1. Here is the emitter of 1, and the emitter of 1 is at AC ground because we have a whatchamacallit, symmetrical circuit. Oh, okay. All right. So our goal here is to relate our output current I out and our input voltage VN, because the ratio of I out over VN is equal to our short circuit transconductance, capital GN. All right. So let's look at a couple of things here. Okay. Since the base of transistor 3 is at ground and the collector of transistor 3 is at ground, I can short these guys out. They're at the same potential. So what it looks like then is R pi 3 in parallel with R naught 3 in parallel with 1 over GM 3. Are we okay with that?
Yeah.
Okay. So let's see here. I'm trying to think about this because I left my solution upstairs. So we look at all 3 of those elements as in parallel. I'm trying to think just real quickly here. All right. What I'm going to do here, just to be arguably on the safe side, is apply KCL up here. Okay. Might be doing this too meticulously as opposed to just looking at a couple of things, but I just want to make sure I'm thinking in a good way, okay? So I can say that I out is equal to VBE3 divided by R pi 3 plus GM3 VBE3 plus VBE3 over R naught 3. Right? This is the current flowing in is equal to the current flowing out. Are we okay with that? Race.
So is R naught one in parallel with those opposite switches?
It is, but I'm gonna get to that in a minute because absolutely it is. Yeah. So what I'm trying to illustrate here, I out is the current that splits up and flows through these guys. And then it's also the current that splits up and flows through this node. It flows through this node right here and then spreads out, right? So I out also has to be this guy right here. Just trying to map things to make it as clear as possible. Okay. So I out, we apply KCL at this other node here. Is GM1 times VBE1, where VBE1 by inspection is VN. And then we have a voltage of VBE3 here. Are we okay with that?
Yeah.
Negative polarity terminal is tied to the negative polarity terminal, positive polarity terminal is tied to the ground. So let's see what goes on with that. So that would be minus VBE3 over R naught 1, I think. And if we look at this guy over here, our original KCL expression, we could pull out VBE3. And this would give us 1 over R pi 3 plus GM3 plus 1 over R naught 3. And coming down here, VBE3 is then I out times 1 over this guy, right? Well, 1 over this guy is just R pi 3 in parallel with R naught 3 in parallel with 1 over GM3. So If we substitute this relationship in to our above one, we have I out is equal to GM1 VN minus I out times R pi 3 in parallel with R naught 3 in parallel with 1 over GM 3, all divided by R naught 1. I'm going to move it to the other side so that I have I out times 1 plus R pi 3 in parallel with R naught 3 in parallel with 1 over GM 3 divided by R naught 1 is equal to GM1 VN. And from this, capital GM is GM1 divided by 1 plus R pi 3 in parallel with R naught 3 in parallel with 1 over GM 3 divided by R naught 1. Which should be extraordinarily close to GM1. Because 1 plus a really small number over a large number is going to look a whole hell of a lot like 1. So, all right, so how do we feel about that short circuit transconductance derivation? Anything seem wild or crazy? We've taken into account every different path all the currents can flow through and all that kind of good stuff. I think we seem okay. Okay. Now we get to our output resistance portion. Okay. So I'm going to make a copy of this and we're going to adjust it. All right. Okay, so my output terminal is what I'm looking into now. Another thing that I have to take into account is that I will be shorting out my input voltage source because anytime I'm trying to measure the output resistance, I short out my input voltage. So we're going to place V1 at ground. Okay. This I out thing is no longer valid. This is no longer valid. So this is what we're looking into to find R out. Are we in agreement here? So my collector terminal is ground. Oh, I'm not in agreement. Let me explain what I mean by that. What about R1? Since this is no longer shorted, we should see R1 between our base node and ground as well, right? Oakley dokley. So really, we could have just left it alone and then put whatever we found in parallel with R1 and called it a day. Okay, so let's look at a couple of things here. VBE1 is obviously 0. Yay, nay?
Yes.
Okay. Which means GM1 times VBE1 is 0. So everything looking down from the emitter of 3 is just R01. Okay. So I'm just going to get rid of all this crap right here. And say that we have R01. All right, so I'm going to apply a voltage source here that I'm going to call V out. Measure my current I out, and the ratio of V out to I out is my output resistance. So if I apply Kirchhoff's current law, I can see that I out is equal to V out over R1 plus, let's see, so this current here let's call this Vx for now. V out minus Vx over R pi 3. Okay. Is there a question about the R pi 3?
I said that would be equal to VBE3.
Yes, so V out minus Vx is absolutely equal to VBE3. All right, so R01 is in parallel with R03. You're absolutely correct there. I'm thinking about applying KCL at emitter, the emitter node here to kind of see what falls out. And so what I mean by that is we have a current of V out minus V out minus Vx over R pi 3 flowing in. We have a current of GM3 VBE3 flowing in. And then we would have a current of Vx divided by R01 flowing out, and a current of Vx over R03 flowing out. Does that make sense? Okay. So current flowing in, current flowing in, current flowing out, current flowing out. Okay. So let's say we have here V out minus Vx over R pi 3 plus GM3 VBE3, which we know to be V out minus Vx is equal to Vx over R naught 1 plus Vx over R naught 3. Are we okay with that? Everybody okay with that? So I know this nodal voltage is Vx, so current flowing out is Vx over R naught 1, current flowing out this way. Current flowing in is equal to current flowing out. This equation right here is useful because the only quantities that it has are V out and Vx, so I can get a direct relationship between V out and Vx, which I can substitute into this guy, so I will have I out only in terms of V out, which is exactly what I'm looking for my output resistance. So I'm fumbling my way through what I need to make this thing work.
Is Vx not negative V out?
Yeah, I don't think that Vx is negative V out.
Negative VB. If Vx was.
Yeah, so that's the problem. So VBE3 is V out minus Vx. That's our voltage relationship there. Okay. All right, so let's manipulate this guy a little bit further. We're gonna have, V out times 1 over R pi 3 plus GM3 is equal to Vx times 1 over R pi 3 plus GM3 plus 1 over R naught 1 plus 1 over R naught 3. Okay. So our goal here is to get Vx in terms of V out. But what I want to do is just to make this less annoying to write down. So I'm going to say that this is the reciprocal of R pi 3 in parallel with R naught 1 in parallel with R naught 3 in parallel with 1 over GM3. Because that's slightly shorter to write than that terrible thing. Okay. R pi 3 in parallel with R naught 1 in parallel with R naught 3 in parallel with 1 over GM3 all to the negative 1 power. And on the left-hand side, this looks like the reciprocal of R pi 3 in parallel with 1 over GM3. And so V out multiplied by R pi 3 in parallel with R naught 1 in parallel with R naught 3 in parallel with 1 over GM3 multiplied by the reciprocal of, actually, let's just do it like this. Is equal to Vx. Which I could now substitute this relationship into here. And then rearrange to find V out over I out.
Of course. No, it does make sense. It's just, you know, when you get like parallel combinations to the -1, I would have no idea how to write that.
In theory, on the test, will we have one this?
Good
time?
God, no.
Okay.
No, of course
I
not.
wanted to make sure.
Yeah.
Would it maybe Do like I out prime, B out prime, or R1.
Quite likely, yes, because we know that it's just going to be in parallel with that, with R1. 100% sure. So Annabelle's suggestion effectively is just saying, ignore R1 because we know that it's in parallel with all of this bullshit, so that it doesn't show up into our equation. To just say it's parallel with R1 at the end, which will make things arguably a little less annoying.
Yeah.
Sure. 100%. Yeah. Yeah. Do we need to actually do the substitution in the last step here? Or are you sure? I don't mind algebra. It is annoying at times, but I can do it if we need to. Or are we at a place where we're comfortable with whatever the next step should be?
I'm comfortable with that. How do you get from the capital DM to ADM?
Okay, so that's a good question. So let's assume that we've taken this the 2 steps further and found R out. Our differential mode gain, ADM, is just going to be negative capital GM R out. I feel, where was it?
It was like in one of these here.
I think that's Connor Haskins' phone. I will have to email him. Taking a lot of notes. Turn that off. Yes, I think.
So it's an open note test.
Mm-hmm.
Does that include our homeworks as part of our notes?
Sure, why not?
Sweet.
Is R out, B out divided by I out?
That is correct.
Okay. Just make it there.
Yes.
Yeah. So it's two separate analyses.
Yeah, you analyze it for the short circuit transconductance, and then you analyze it for the output resistance.
Right. Okay.
Using the proper rules for both measurements.
Yeah, I had a problem with homework too, because I was trying to do both at the same time.
Can't do it.
And you can't.
You literally
B
cannot.
out is shorted.
Yes, which means you see an infinite resistance because, yeah.
Yeah.
So you're talking about the rules when you're talking for the short circuit, the R out. Can you write those down? Like, what do you ensure that?
Okay, writing it down is going to be annoying, and I feel like that should be in your notes, but let's talk about it, okay? So here we did our short circuit transconductance measurement. So what I did is I shorted out my output terminal, and I found the current flowing through that short circuit. The ratio of I out divided by VN is our short circuit transconductance, okay? So to be clear, all you do is short circuit the output terminal and then figure out what current flows into that short circuit. And then take the ratio, relate that output current to the quantity VN, and you're done. Luke, you're raising your hand, I think.
Why didn't we short the base between the collector and the base between?
This short circuit right here, because this is at ground and that's at ground, so why not? They're the same potential. It allows me to illustrate that all 3 of these things are connected in parallel, which is effectively what this relationship right here tells us. And it's why we see all 3 things in parallel here, and then again. We can still treat them as if they're in parallel without that short directly between the base and the collector, because it's all they're all located between that emitter node and ground. Go back to the I out equation. Kelly, is that what you're referring to? With Vx. So you mean this guy over here? Okay. All right. So let's talk about what I was doing here. This is where I was measuring the output resistance. And I now realize that it's confusing because I have two I outs that mean two different things. So I apologize for that. It literally didn't dawn on me until this exact moment. This I out right here is an entirely different I out because it's the I out that's being supplied by this test voltage source. All we're doing here is what we did in circuits 1 by applying a test source and using that to measure the Thevenin resistance. It's just, these are ugly as hell, but it's nothing different than what we did in circuits 1. Okay, so we short-circuited our input terminal, which is why we were able to analyze transistor M1 and say that it only looks like R01 from the emitter to ground. Okay. So when we do our output resistance analysis, we always short out our input signal and then look in through our open circuited output terminals. And if it's complicated enough, we can apply a test source method to determine that resistance.
This all basically boils down to making equations, ratios.
Yeah. Algebra sucks. And
That's what's been hard for me is like.
I think that's what's hard for a lot of people is seeing something like this and then recognizing that just means there's resistors in parallel.
Probably to the values, the actual problem.
Yeah. Jordan, are you raising your hand or stretching? Just stretch. Okay. Race. Homework 2, problem 1. Okay, so do I have the gain listed as positive or negative? I feel like the gain is supposed to be negative because the gain of a cascode is supposed to be negative. So that should be that numerical value, but with a negative sign in front. And I apologize for missing it.
Hypothetically on the test, would that just be like a -1 if everything else was correct?
Yeah, it would not be a big thing whatsoever. Yeah, because it says the cascode is effectively supposed to behave like a common emitter amplifier, which definitely has a negative gain, but with a really large output resistance. That is its absolute function. So the cascode gain equation should wind up with negative gain. So I apologize for missing that.
For our common mode rejection ratio, we have a formula that's 20 log and the absolute value of AV comma D. What is AV comma D?
That is the differential mode gain. I'm using shitty notation. Yeah,
Okay.
ADM, the differential mode gain. I apologize for that as well. So there's a differential mode gain, there's a common mode gain, and then there's a differential mode, or no, common mode to differential mode conversion gain, and they all represent different things because electrical engineers are assholes. Yes, so D is for differential, C is for common, and I apologize for mixing up notations there. I got to get more consistent. I sincerely apologize.
I was double checking before I
Yeah,
had the numbers.
seems
in the
very
problem
reasonable.
Before I was gonna plug them all in.
Yep.
So ADM is the differential mode voltage gain.
Yes. A is gain, DM is differential mode.
Right.
And at this point in the class, we are only dealing with voltage gains.
And that would be V out DM divided by
V in DM. So V out minus V out 1 minus V out 2 over V in 1 minus V in 2.
I probably have that written down in the notes. I think I remember you saying that before.
So just as a heads up, if you can suffer through this homework and have it make any sense, the exam should be easy. That's my goal.
Okay.
All of the problems should be easier than what you had on the homework. Definitely the analyzing a differential pair using a half circuit thing should not take 35 minutes, because then we don't have room for any other questions. Julia.
It's gonna be hard problems, like,
I honestly don't know if it's going to be like 5 problems, but it's not going to be wildly long or anything like that. It really just kind of depends on what different things that I can ask you.
I don't know which one did this last one. You don't do like a section of theory.
So I'm not gonna, because these guys were all terrible at the theory questions last quarter. Any theory questions that I ask are actually going to be on the take-home test. And then the expectation there is that you will literally do some research from textbooks, online articles and stuff like that to answer the questions. As opposed to you having to give me the theory results and then whatever it is, because that seems how it worked on the in-class portions last quarter. So let's see. So it's going to be due a week after you take your in-class portion. So if Monday is the 4th, then that seems like 4/11 to me, if my mental math is correct. Is that right? 4 plus 7 is 11, right? Yeah, okay. And it'll be a few theory questions and then a single design-based problem, where I'm going to ask you to design a differential pair MOSFET circuit with a specific gain constrained by a specific power budget. And your power budget thing is effectively telling you what your tail current is constrained by, because the power budget is just your tail current times VDD.
Makes sense to me.
Yeah, that's the maximum current that you can have flowing through either of your paths. So yes, ma'am.
Are you still considering posting music channel?
I am. I'll probably do that shortly. I have a meeting with Dr. Batari after this. I'll probably get around to doing it. I need to ask his permission technically, because he and I worked on it together. And so if he doesn't want me to do it, then I'm not going to do it. I don't feel like he's going to say no, because he has no intention of ever teaching this class again. So he was rather pleased to not have to do it. So anyway, for what I feel like are obvious reasons. So anywho, but yes, I will absolutely do that.
So would you say the biggest part of this test would just be finding capital GM and RL?
Yes, but to me, the biggest thing of this test is recognizing things that are familiar so that you don't bog yourself down.
Okay.
And what I mean by that is being able to look at a portion of a circuit and say, oh, well, that's a current source, or oh, that's a cascoded current source, or oh, it's a current source generated by a resistor, and then knowing how that works without having to derive everything from scratch every time. Because if you have to derive everything from scratch every time, every problem's an hour-long problem. Whereas if you can look at it and say, okay, so looking down, I see this thing which has this output resistance. Looking up, I see this thing which has that output resistance. Those two things must be in parallel. That just eliminated a ton of work. Then you only have to concern yourself with a short circuit transconductance calculation and you have the gain.
So if I was like hypothetically pushed for time and I didn't have time to calculate big GP or big GM. I just, 'cause a lot of these are.
It does simplify to just GM of the input thing an awful lot. So let's talk about which ones we know that explicitly for, okay? We know that explicitly for a cascode. We know that explicitly for anything that's common emitter or common emitter / common source looking. For a source follower in the homework, you proved that it should be, so that would be a common drain or common collector amplifier. It should actually be negative GM. So really the only thing that you're not sure about would be something that would be common gate / base related. Everything else, you have a pretty solid idea that it's going to be either positive GM1 or negative GM1. And I'd be willing to bet just based off of your knowledge of, so a common emitter amplifier has a gain of negative GM R0 in parallel with RD. And a common gate amplifier has a gain of positive GM R0 in parallel with RD. So I'd be willing to bet that the short circuit transconductance is negative GM.
Yeah. What is the VIDM stuff?
What do you mean the VIDM stuff? That's very, very vague.
There's a lot of deriving with like the voltage IDM.
I'm not expecting, so once we get to a half circuit, that no longer matters. So that was before we had developed the concept of half circuits and all that kind of stuff. There's let me say another thing. There's not going to be any DC operating point for differential pairs. So that hyperbolic tangent thing or anything like that, that's not going to be on. Your calculators, at least mine, I don't see a hyperbolic tangent button on it. So I'm just going to assume it can't do it. Do not dissuade me or whatever from that opinion if you're smart. You use an HP though, don't you? Yeah, that's why. Yeah, you're the only person. Well, I mean, it may be on here somewhere.
About the April Fool Day kneecap.
I thought about coming in with a stack of old tests for this class printed out and being like, okay, well, you guys are ready for your exam. And then my wife was like, you're going to get murdered.
You were like, hey guys, April Fool's the test today.
Yeah. All right. Is there anything else that we need to review? Did you say something? Okay. No, legitimately, if you did, I'm happy to do it. I just didn't hear.
No, I.
Okay. Okay.